All right, let's go ahead and talk through some of the information necessary to work on test one. So one of the guaranteed test questions is this first one with the weighted average. This one will also be on the final exam. So this is an important question to me. I want students to know how an average is calculated. So with this one, I've got, obviously a modified version of the question where the numbers have been scrubbed out. But I do have an example in the corner. So you want to think about these. These can be randomized. So whatever this grade is going to have a percentage associated with it. So let's say that it was something like a strange number, say 42% here, and say that this student had a 90 on that. Then in order to find the contribution of this category of test averages, then we would take 42% of 90. The easiest way to do that is turn 42% into a decimal, so 0.42, and then multiply by the grade of 90. And then that's going to give you some partial points. Okay, so we would get, looks like 37.8 points from that. And that would mean that that was all the student did, that would be their final average. But there are other categories. So let's say the final exam grade is 25%. And let's say that they make an 80 on this. Then in a similar way, we want to take our percentage, work it as a decimal. So 0.25 is easier usually to put in your calculator. Then multiply by the points in that category. And we would now have another 20 points. And then we would do this for everything that's left and eventually find the total. So numbers will be randomized, the percentages might be randomized, but this is a process that I want you to know. You have a full worked out example in other videos and in your notes. Okay, so one that is potentially on the test. So the rest of these are randomized, and I don't know for sure who's going to see what. The only one that was absolutely for certain for everybody was the first example. Okay, but for this one, this was week 1A, question 6, and we were looking for displacement. And we need to remember that displacement is the change in position from starting and ending for a person for a path. So, basically how far away did you end up, or how much did you change your place if we break this down into, root, prefix, suffix. Okay, so what we have to think about here is we have numbers where the students are going back and forth. And so they go a certain amount in one direction, and then they go a certain amount in the opposite direction, and then they turn around again, and then they turn around again, and they're just basically walking back and forth. I have no idea what these numbers are. Then what we want to think about is, say one of these measurements was changed by a factor of, let's say, 0.55 or something. It doesn't really matter what. Then I have no idea how much that's going to affect the final answer because I don't know what any of the other numbers are. So there's no way for me to guess from that. So for one of these being changed, I can't guess. And even if we tried to group these together, so sometimes when you would work them out, you would take the ones in the same direction together. So in this case, say the ones that are positive, and then the ones that are negative, and we can sort of group these and bring them together. So minus this total, so notice that there were two subtractions, but I put them in parentheses and subtracted together like this. Now you might think that if both of the measurements in one direction, say both of these were doubled, or multiplied by 0.5, or multiplied by 3, or whatever, that you'd be able to predict what the answer would be. But you have to remember that we have no idea how big or small the other number was. The only thing that would consistently give us a reasonable answer would be if every single measurement was doubled or tripled. And then it would work out that if everything was doubled, then we could factor a 2 out of all that, and then the answer would change by that amount. So be careful with these, especially any question that has addition or subtraction. Unless you're changing basically everything, most of those questions aren't going to make sense. Okay, so in the next one, we have to pay attention to the word speed. So we had from week 1A again, I believe it was question 7 and question 8, talked about speed and velocity. So speed around a circular track, that's something that we want to think about. Person's going around in a circle. Speed pays attention to the full path around. It doesn't care about direction, just wants to know how far did you go in however direction or whichever way you went between two times. And so the fact that it's a circle wouldn't matter. We just want to know what's the total distance around that circle. By definition, speed is distance divided by time. So it's a scalar, we're only worried about numbers. Then to sort of make a formula out of this, we don't normally, when we say distance, a lot of times we really mean displacement. So we have to be really careful with these definitions. So I'm going to put D in quotation marks. Often when we say we use D in a formula, it really means displacement, but that's not going to hurt anything here. Okay, and then divided by time. So now let's think about what this is going to do. So this is the first equation where we can change different things and get different sorts of answers. So let's say that the distance was changed by a factor of 0.5, but then the time wasn't changed at all. Then if we're trying to figure out the factor by which the answer would change, it's basically the ratio between your new answer and your old answer. Well, in your new answer, it's going to have the same time as the old answer used, and so those effectively have a ratio of 1 or they don't change. And so that's where we can use this to our advantage. I have no idea what numbers these were. Technically, you can look back at your old examples, and I've included one here, and you could work this out, and then if the distance changes, well, you could go to the question, multiply the distance by whatever decimal, and then, work it through and see what happens. But it's not necessary. You can look at just the formula and see what's going to happen. So let's say that I said that the displacement changed, sorry, the distance here changed by a factor of, say, 0.5, just because it's a nice, easy number to work with. So then I would have 0.5 times that distance that I would work through the question, and then t would be the same. And so what I would end up with is I would get a new speed that would end up in a ratio of 0.5 over 1, or just the factor itself. What's different though is if I look at where the time is in the formula, that's going to do something maybe unexpected. So if we only change the time, so if my time here is changed to be half the amount of time, and then I want to work the question again, well, because the distance in this different example would be kept the same, then they'd be in a ratio of 1, right? So it's not going to affect the new answer. And what would happen then is I could take 1 divided by the ratio of the time. So just that factor that was introduced in the question, I would have 0.5. So I would actually end up with the reciprocal of this number. So 1 divided by 0.5 is 2. So one of the major things to look at here is the placement of the variable. You want to see where these are in the formula. If the variable doesn't have anything fancy going on, if there's no exponent on it, no square root, there's no like addition or subtraction or extra steps, it's not multiplied by anything else, then we end up getting the factor back as an answer. But if the variable that you're talking about, if the time is changed by, whatever factor, then, the time may have exponents on it or could be under a square root, or in this case, could be on the bottom of a fraction. And then that means that it's going to change in still a predictable way, but not one that's quite as easy to see. You have to plug in and work some numbers and see what it looks like. Now, the next question is almost the same, but here we're looking at velocity and a circular track. So this was still from week 1A. This was question 8, the follow-up to the previous one from our previous work. Velocity is usually represented by a lowercase v, is displacement divided by time. Okay, and so typically that would be d over t. Something to think about here, though, is that your velocity is a vector. And so that means that if we're dealing with a circular track, so I'm really going to stress this part, a circular track, then we can actually be a little bit more specific here. You go around in a circle, you end up in the same spot from where you started. So technically you haven't accomplished anything, you haven't gone anywhere. Your displacement is 0. And so we would end up with 0 divided by time. So what we want to think about now is what happens if the question is asking us about these different variables. So let's say that the question said that your displacement was changed by a certain factor, okay? If your displacement is changed by a factor of 0.5, well, it's half a zero, right? Hopefully you said zero, right? And so this does not change. So you always have an answer choice that says something like does not change or does not make sense to calculate. Sometimes those are combined and sometimes they're separate, but this one would not change. So the distance around the track wouldn't matter. The size of the track doesn't matter. If you end up in the same spot, you're always going to get zero, so the answer wouldn't change. Now, the time, if we look at the placement of that again, looks kind of like what we already saw. So if time is cut in half, so we're dealing with 0.5, half the time, then again, we want to look at this and see where the variables fall. Um, well, we would have 0 up top and divided by half the time. Look, well, that's going to make 0 again. So we want to think about that, right? There's still a 0 in this, and so this does not change. So displacement, when you're going in a circle, is going to be 0 no matter what. Okay, then last one from this first week. We've got roughly 4 of these from each week that pop up as potential test questions. We have a ball that's going to reach maximum height. So we want to think about what we know about this and what's going to cause the ball to do anything fancy. So we've got gravity is going to be the acceleration that tells us how this ball moves, right? So it has some starting velocity, and then it slows down due to the acceleration from gravity, or eventually stops for just a tiny portion of a second and then comes back down again. So the only thing at this point that we would know about acceleration and velocity is that acceleration is velocity divided by time. Okay, then we want to keep in mind that this acceleration is going to happen because of gravity, so we can kind of bring that around a little bit. And so gravity, we could factor out if we didn't have this information, if for some reason we're doing an experiment on Earth or Mars or something, then we could actually use similar information the other way around and calculate what that gravity would be. Okay, but this question says that we're calculating time. So I'm going to look at where there's t in this formula. I need to solve for that thing. And so we have some options. You can kind of think about this as being like a proportion, right? Take the g and stick it over 1. So let's do that in a new color. Let's say that this was over 1, and then cross multiply. You'd have first v equals g times t. And then if we were trying to solve for t, then we would want to divide and move that around. So we divide by gravity, and we get that time is equal to velocity divided by gravity. Okay, so now let's see what would change from this, and let's see if potentially if there's any extra information, because there might be. So from these different variables that we've got, if the velocity changes, so again, let's say that we had some velocity, we changed it to some ratio, we were trying to now recalculate this with half the velocity. Once more, you could copy this question, use actually half of velocity, calculate your new answer, and find the ratio between the two to figure out the factor by which it changed. Or we can think about where v is in this formula, use a little bit of brute force logic, and we can work through and see what's going to happen. So velocity is now in a ratio of 0.5 compared to what it was before. It's smaller, it's half. If gravity is the same as what it was before, then the ratio of the new gravity versus the old gravity, we'd have 9.8 divided by 9.8 if we were on Earth, would give us a 1. And so this would end up giving us 0.5, which would be the same as the factor itself. So then that would end up being the answer we were looking for. Okay, well, let's say that gravity somehow changed. Now that would be strange, but again, we could have a question where we're talking about something, on the moon or on Mars instead. So let's say gravity got cut in half. Think about where gravity is in this question. If the velocity is left alone, then the ratio of the new velocity compared to the old velocity is 1, and so we can plug in 1 for that. Then the ratio of the new gravity compared to the old gravity is 0.5, and so we have 0.5 here. So because the gravity was in the bottom of this fraction, we end up getting the reciprocal to this factor, whatever the decimal was for your example. And so we'd have 1 divided by whatever factor, which in this case is 0.5, and we would get 2. Okay, so then now moving into the second week of material. This would be week 1B. And question 3 in particular for this one. So students looking for an x component of a velocity. You can use this as v for velocity, or you can use a for a first vector, because often we'll have multiple vectors and deal with them together. There's a few different ways that you can show this formula. From your formula sheet, because this will work for any style of vector, it's just listed out as a, so like vector a or the first vector in case we have more than one. If you want to find the x component of that, then it has an x subscript. You take the original magnitude of the full vector a, and then with the way that we draw these out and the way that the axes are labeled, then we would end up with cosine of an angle multiplied by that information. Okay, so there's our formula. And then we think about some of the things that could change with this. If the original magnitude of the vector changed, then let's say that we had a vector a and then we modified the number to be half of a, and we want to see how it's going to change the answer between the two examples. Well, think about where this is in the question in this formula. Um, Theta, we don't know what that is, but whatever cosine of theta is, if theta stays the same, it's the same cosine of theta for the decimal part there. And so those are in a ratio of 1, and so technically what we would have here is 0.5 times 1. So we get 0.5, which is the same as the factor that would have been given, or whatever the factor was for your question. Then here's the unfortunate thing. When we look at the other side, let's say that we were given an original theta, and then we want to deal with half of theta. Well, it's something tricky is going to happen here because you're going to have a as a ratio of 1 to 1, new a versus old a. So you think, okay, well that's 1, and then that's times cosine. And then the unfortunate thing is cosine is a little bit unpredictable. So taking cosine of half of the angle is not going to give you an easily predictable number. It's not going to be easy to see by how much that's going to change. Um, In fact, depending on what the angle is, if we were to go the other way and say double some angle, then you may end up going from a positive answer to a negative answer. And so these really just aren't going to do consistent things. So messing with the angle is not going to be predictable or easy to calculate. Okay, then in the next one, we want to look for something called net force. And we've talked about this before, but net force, kind of like net pay, different dollar amounts that you're paid and taxes and things that come out end up working with and or against each other, depending on whether you've got bonuses or insurance to pay or whatever. But net forces are going to do something similar. They're going to push and pull and work with each other and against each other, depending on how they're arranged. Now, in this question, two people are helping to push something, and we're going to assume that they're going to be smart enough to help push in the same direction. And so then that's going to tell us normally there's not a direct formula for net force. But because we've got two people helping to push, then we're going to assume that they're, like I said, smart enough to push in the same direction. And so we would have just F1 plus F2. Okay, so something we want to think about here, anytime basically there's addition in the formula and you're trying to see how it's going to change, you've got to be careful. If we were to change just one of these, so let's say that I take the force from one of the people, and since I don't know any names or anything, I can just say the first one as an example. And let's say that I multiply it by some factor. Then I have no idea what that's going to do. Because just changing one of the numbers. I don't know how big or small the other one was. I don't even necessarily know which person I'm changing. I have no way to predict what's going to happen to my answer. So that's not going to work. But let's say that the question asks you to change all of the forces. So just F1 and F2 are changed by some factor. So then I need to include that factor though. Let's say it's changed by 0.5 like I've used in the other examples. And this is for F1 and F2, so all the forces are adjusted by this factor. Then what happens is you're going to end up with that factor affecting both of these things, and that means the ratio of your new answer compared to your old answer is going to end up being the same as that factor. All right. So going a step further from that, again, you want to pay attention to what's involved here. We have a combination of formulas that go into solving this one if you peek at the example that we had before. So we've got the net force, the two people are helping to push, is going to be F1 plus F2. And then from Newton's second law, the net force is equal to mass times acceleration. And so what we can do is we can take this whole chunk of stuff and we can put it in for net force. Okay? And so what that's going to tell us then is that F1 plus F2 is equal to mass times acceleration. All right, now let's read the question carefully. This is wanting us to find acceleration, so that's here, which means that I'm going to have to divide by mass. And so my formula, acceleration can be found by adding these forces together and then dividing that sum by mass. Okay, so we want to think about what this is going to do from different types of changes. So once again, if you change only one force, then we don't really know how that's going to affect the total of the forces exactly, and then we're going to get stuck. Okay, so if we change both of the forces, so F1 and F2 are adjusted, then we at least know how the net force is going to change, similar to the previous example we looked at. So that's going to tell us that we would have half of the sum here. Then we look at the ratio of the new answer compared to the old answer. The ratio of the sum compared to the old ratio of the sum, we're going to end up with 0.5. The ratio of the mass to the old ratio of the mass is going to be 1. And so this ended up being 0.5 over 1, or just the factor itself. Okay, and then the last reasonable way that this question might be changed, and to try to see what's going on, let's take it, I guess, the other direction. Let's say that the mass is changed by some factor. So the mass, we come back and take half of it, and we work the question again. Like I keep saying, in any of these, you can go back to the original, just make that modification to it. So in this case, we take the 12.33 kilograms, we could cut that in half, work the question again, see how the answer changes. Or we can reason through and see what we think. What that's going to tell us then is that if I'm calculating for the acceleration, the ratio, the sum of the masses compared to the old sum of the masses is going to be the same, or sorry, forces to the old forces is going to be the same. So that's going to be ratio of 1. And then the new mass is half as much as the old mass, and so I'm going to have a ratio here of 0.5. And because of the placement, you see the m was on the bottom here, then we're looking at the reciprocal of whatever ratio you have. So I've got 0.5, but maybe you have 0.683 or whatever, and it's going to be in 1 divided by that or the reciprocal of it. So for my example, the number I've made up here, this is going to turn into 2. All right. Then last one from week 1B, we've got buoyant force, which is the force that comes from a solid object displacing a fluid. the weight of that fluid pushes back against the object and gives it a certain amount of lift. If the object is light enough, or if it's the right combination of mass compared to volume, we'll learn about that a little bit later. But if it's the right ratio of mass and volume, then it can float on top of water. Okay, so in most of these questions, you're not going to know the weight of the object directly, but we've learned and used in a few different places that weight can be found by taking mass times gravity. So buoyant force can be mass times gravity. Okay, and so let's think about the things that we can change from this. Let's say that the mass is updated, and so the old mass is changed to be half of whatever it was originally. Then think about how that's going to plug into this formula. So the ratio of the new mass compared to the old mass is half. Gravity wouldn't change in this case because it's not being talked about. So technically it'd be 9.8 to 9.8 or 1. And so that's going to give me 0.5, which is my made up factor here. Okay, then the weird question here is, what if gravity changed? So what if we were talking about an alien planet where gravity was only half as much as it is on Earth? Well, then the mass of the object, if that's not changing, then the new mass compared to the old mass is a ratio of 1. Then the new gravity compared to the old gravity, again, if we were to stack these into a fraction and simplify, we'd just get back a half, and we would actually get the same answer. So in either of these cases, because it's just two things multiplied together, we end up getting just the factor back. Okay, and then part C, week 1C, last part of module 1. We want to work through a few questions here. We've only got a few left. We were looking at tensions, and we had this symmetry here. So a worker was standing in the middle of the platform. And so it's very small, but there's a picture here. We can see there's a worker in the middle. And then because of the symmetry, it's not lopsided either way, but you're going to have the same amount of force on the left side of the picture compared to the right side of the picture. The tensions are going to be the same. And so we want to think about this. It's kind of small, so I'm going to label this again, but it was T1 on the left-hand side and T2 on the right-hand side. But let's say that a new version of this is set up and the worker moves to the left or to the right. And so I'm gonna, sketch out a picture here. And let's say this time that the worker is over here on the left side. Then what's happening, if we cut down the middle, this is off center. And so, the platform itself is still being split evenly on the two tensions, but now more of this worker's weight is over here on this side. So then now T1 is going to be much bigger than T2. So I'm going to try to do quite literally by making a bigger T1 than T2 from the left side compared to the right side. Okay, and then let's say the opposite happened. So the worker goes on the other side. And then again, we think about, where we used to have symmetry, everything was split evenly down the middle, but now the worker is on this side, more of his weight is going to be supported on the right-hand side where we labeled T2, and less of it's going to be on T1. And so comparing left and right, then we can see what's going to happen here. Now, if the worker stayed in the middle, then we would still have balance where T1 is equal to T2. Okay, then one of our big topics from this week was talking about friction. So wouldn't be complete without one of those questions here. Now, by definition, the main thing that we know about friction is that the force of friction is equal to mu, which is the coefficient of friction, times normal force. Now, typically, you're not going to know what normal force is. And so we would have to go and find that. And normal force would be equal to the weight of the object if you had that information. Typically, we haven't been given that, so we've put it together from mass and gravity, kind of like what we did earlier for buoyant force. And so now you can take all of this stuff that normal force was equal to, and you can plug it back into the formula, and we can sort of combine this. And instead of working through two pieces, we can see it all at once. So if we decide to, we can combine those and say that the force of friction is equal to mu times mass times gravity. Okay, and then let's think about the different changes that might come from this. So let's say that there's a new version of the question and mu is adjusted by some factor. So whatever mu was is changed to be half of mu. Well, the ratio of the new mu compared to the old mu is going to be that decimal, so 0.5. If the mass is unaffected, it wouldn't be mentioned to change two things at the same time here. Then the new mass compared to the old mass would have a ratio of 1. New gravity compared to old gravity have a ratio of 1. And so from this, we get just 0.5. Now, I'm hoping that you can kind of see the placement of these variables and see that nothing super fancy is going on and guess on your own what the rest of these are going to do. But I'm going to work throughout the answers just to show specifically. So let's say the original mass, whatever it was, is adjusted to be half, by some factor, and I'm picking 0.5 on these examples. If you want to, you could go back to the original question, find half of the mass, plug that in, work the same stuff, see how it changes. Or we can reason through and see what we think. Okay, if mu is unaffected, then the ratio of the new mu compared to the old mu is 1. The mass was changed by this factor, so the ratio of the new mass compared to the old mass is that decimal, 0.5. Then if gravity is unchanged, then new gravity compared to old gravity would have a ratio of 1, and then altogether the answer would end up changing by whatever the factor was, in this case 0.5. Then it would be kind of a strange question, but let's say that we're told that gravity changes. So whatever gravity used to be, we're assuming probably Earth gravity, is cut in half somehow. Then think about the ratios of the unchanged variables. New mu compared to old mu, new mass compared to old mass. We would have so far 1 times 1. Then the new gravity compared to the old one is adjusted by this factor, so 0.5. And 1 times 1 times 0.5 is in fact 0.5. So it would be whatever factor that you were given. Okay, then one of the other major things we talked about was springs. So springs are best described from what we're looking at by Hooke's law. So the force on a spring is equal to the spring constant multiplied by the change in length. Now in a later section, change in length is represented by x, but in this part of the textbook, it's still just delta L. So we're going to keep it that way. Now it does say in this question that we're looking for the spring constant. So we are going to want to solve for that first. And so if you look, spring constant, it's related to German, so think constant with a K. Then we want to solve for this thing right here. And so we would divide by the change in length. Okay, then that's going to give us that K is equal to the force on the spring divided by the change in length. Okay, then without really knowing how this is going to be changing, we do know that the force, it says we're given a mass right here, right? So the force on the spring is going to come from the mass that's hanging there. But we do have to be careful because that force itself is not the same as the mass. It would come from the weight of whatever's there, which would be mass times gravity. So our fully fleshed out formula, you're going to take this stuff and plug it in, and then we would have that K is equal to mass times, sorry, my pen's messing up there, mass times gravity divided by change in length. Okay, so let's see what we can do with this from here. So, thinking through the different parts, let's say that the mass was changed. So we have 0.5 mass compared to whatever the original was. Then the ratio of the new mass to the old mass is 0.5. Sorry, that's just a little bug that, there we go. All right, but the ratio there is 0.5. Gravity would be unchanged, so that would be 1. Change in length was, as far as we know, unchanged, so that would be 1. And so these 1s aren't really going to do anything, and we would get 0.5, or just the original factor back. Okay, then it would be strange, but let's say that gravity is changed by a certain factor. So we had gravity, and now we've got half of gravity, because why not? Then the mass would be in the same ratio, 1, and same value it had before. The change in length is unaffected, so it would still be 1. And then gravity, new gravity to old gravity has a ratio of 0.5. Because that's still in the top of the fraction, then that's going to give us just 0.5, or whatever factor that you had. Okay, and then our final variable, the last thing that might reasonably change would be the change in length. So let's say that from the original change in length, the delta L, we end up with half the change in length. Maybe it's a different spring, maybe it's a different material, whatever. We have no additional information here, but just the example question, the numbers we're looking through, delta L is half of what it used to be. Well, the mass is unchanged, so new mass to old mass has a ratio of 1. Gravity is unchanged, so it has a ratio of 1. And then delta L here on the bottom is 0.5. So because this is a little bit more interesting in the placement compared to the other ones, we get 1 over 0.5, or the reciprocal to whatever our factor was. And in this case, this is going to become 2. Okay, then last one in the group. So this is the last major thing that we're going to talk about for Module 1. Again, we've got a spring in this question. We have some partial information. We are not given a spring constant, and we are not told to find one. But assuming that a spring constant is going to be held constant, because normally they should be, then we can actually set up a proportion. Some mass will cause a corresponding change in length. And if you had the right values and they were the correct units, you can make this into a spring constant. Even if it's not converted, you can make it into something like a spring constant that is still useful information. You don't care in the slightest bit what that number is. I just know that whatever it would have been will be equal to whatever our second scenario is, where we can stack mass and change in length in a fraction. Okay, so here it says we're calculating the new mass. Well, that to me says that we're looking for M2 with the way the question is set up. And so if I want this thing, then it kind of looks like a proportion, but I don't want to cross multiply everything because I don't want to mess up my my M2 that I'm looking for. So instead what I'm going to do is multiply both sides by delta L2, change in length 2. And what that's going to do is it's going to cancel from this side. It's going to bring it to the numerator over here. I'm going to try to fix my handwriting, 2. And so then that's going to tell me that the new mass is equal to the new change in length multiplied by the old mass divided by the old or original change in length. Okay, so there's our formula, and again, you can see placement of different variables. It has the general shape similar to what we had on this one, right? 2 variables on top, 1 thing on the bottom, 2 variables on top, 1 thing on the bottom. So let's see what we can do with that. Let's say that the change in length 2 for scenario 2 is adjusted by a factor of, let's say, 0.5, because that's what we've used on all of them so far. Then think about the ratio of the new value compared to the old value. Well, we don't know what it was, and it turns out it doesn't matter, because if we stack them, and as long as they weren't zeros, then they're going to reduce down and give us that factor back of 0.5 here. Don't know the mass here, but if I don't change it, then the ratio of the new mass compared to the old mass from this example is the same number. It's going to have a ratio of 1. And then here, this one's unchanged. So technically, I mean, you could say it changes by a factor of 1 or has a ratio of 1. And then I think it's fairly easy to see that that's just going to give the factor back. So 0.5. Okay, then let's say that in our scenario, this variable is changed. So M1 is adjusted by a factor of 0.5. And again, you could go through this, cut the certain mass in half, run through the example, see what answer you get, compare the new answer to the old answer by dividing, and then, that will give you what you're looking for. All right, but let's try to do it through logic and formulas first. So the delta L2 is not affected in this example, so it would be in a ratio with itself, and it would be 1. The mass is changed between our different numbered examples, and so the ratio of new to old would be 0.5. Delta L1 is not said to have changed, so we assume that it wasn't, and it would be in a ratio with itself of 1. Well, given that this variable is on the top and there's no exponent or addition or anything else, then I think it makes sense, hopefully, that you end up with just whatever the factor was again. What you want to keep in mind is that these are going to give you weird answers when the variable we're talking about is in sort of a weird place or has weird features. So like this one, if delta L1 is adjusted to a new question like this that is half as big, then because of its placement on the bottom of this fraction, we're going to see something more interesting. So delta L2 is in a ratio of itself of 1 if it's unchanged. The mass is going to be ratio of 1 if it's not changed in this example. This time we will be only changing the delta L on the bottom, delta L1. So our new version of delta L1 is 0.5. And so what that's going to give us is technically the reciprocal to our ratio. So for this one, I picked an easy number to work out, but 1 divided by a half is going to give 2. All right, and so this should be most of what you need, aside from the conceptual type questions, like the short answer definition type questions. But this should be pretty much all of the math type stuff you need to know for the first test.